So welcome. So this video we talk about numerical aperture and acceptance angle. So now consider cylindrical fiber. It consists of core of refractive index n1 and gladding of refractive index n2. And let n0 be the refractive index of the medium, so in which the optical fiber is placed. The incident ray travels along AO and enters the core at an angle I to the fiber axis. So the ray refracted along OB at an angle theta is the core. So further proceeds to fall at a critical angle of incidence pi c equal to 90 minus theta on the interference between core and gladding. At this angle, the ray just moves along BC. Any ray which enters into the core at an angle of incidence less than I, so will have a refractive angle less than theta. So hence the angle of incidence pi equal to 90 minus theta at the interference of core and gladding will be more than the critical angle. Hence the ray is a totally reflected ray. So thus only those ray which passes within the acceptance angle will be totally reflected, that means internally. So therefore the light incident on the core within this maximum external incident angle IM can be coupled into the fiber to propagate. So this angle is called as the waveguide acceptance angle. So the angle IM is unique only for a particular fiber in a different form of fiber to fiber. It depends on the material and the core diameter. So next, calculation of numerical aperture. So consider longitudinal section of fiber, and as I already told that, and we know that n0, n1, n2 are refractive indices for air outside the optical fibers, the core and gladding respectively. See, in the light ray travels from A to O and enters a core at an angle I to the fiber optics, and this is acceptance cone. The ray refracted along OB at an angle theta in the core. So the further proceeds to fall in a critical angle of incidence pi equal 90 minus theta. This angle ray just moves along the BC. And any ray which enters into the core at an angle of incidence less than I will have a refractive angle less than theta. So therefore hence the ray is a totally internally reflected ray. So the waveguide acceptance angles are the calculator. So applying Snell's law, at a point of entry of ray AO we have n0 sin I equal to n1 sin r. So therefore sin I equal to n1 divided by n0 sin theta. That means sin I equal to n1 divided by n0 root of 1 minus cos square theta. So applying Snell's law at a point P on interface, n1 sin pi equal to n2 sin 90 degrees. So that means sin 90 already we know that is a 1. So sin pi equal to n2 divided by n1. So sin 90 minus theta equal to n2 divided by n1. So therefore cos theta equal to n2 divided by n1. So substituting equations, both the equations we get I equal to sin inverse root of n1 square minus n2 square divided by n0. So if the refractive index of air n0 equal to 1, then the maximum value of sin I is given as sin I max equal to root of n1 square minus n2 square. So where n1 and n2 are refractive indices of core and gladding respectively. So already we know that the numerical aperture is definition is the same of sine of the acceptance angle of the fiber. That means Ne equal to sine Im. So that means root of n2 square core minus n square gliding. So that means Na equal to sine Im equal to root of n1 square minus n2 square. So Na increases with the increases acceptance angle, and the refractive index, it is ratio of the refractive index difference in the core and gliding to the refractive index of the core. So that means del equal to n1 minus n2 divided by n1. So therefore relation between Na and del, so we know that Na equal to root of n1 square minus n2 square. So therefore Na equal to root of n1 plus n2 into n1 minus n2. So finally we get Na equal to n1 root of 2 del. So therefore Na equal to n1 root of 2l. Thank you. We discuss in next session.